By 2026, deep learning architectures have secured superhuman accuracy in highly specific, narrow domains. In medical diagnostics, specialized systems process scans to spot retinal diseases with over 95% accuracy, surpassing human clinical performance. Yet these same frontier models, classified as emerging AGI, exhibit a glaring paradox. They can parse millions of documents and pass the Turing test, but they lack the basic common sense of a human toddler. They struggle to navigate a physical kitchen or understand why a stacked tower of blocks might fall. Scaling current architectures by adding trillions of parameters yields diminishing returns in logical reasoning. Reaching artificial general intelligence requires a change in the underlying architecture of how models process reality. Genuine intelligence requires physical intuition. When a robotic arm releases a sphere, an intelligent system uses a predictive bounding box to calculate the trajectory and impact point through physical simulation, anticipating reality before it happens. The industry is moving away from pure language generation. The focus has shifted to world models, systems engineered to simulate the causal physics of reality rather than just mimicking human speech patterns. Intelligence is not measured by eloquence. It is defined by an intuitive, grounded grasp of physical mechanics. The barrier to this physical intuition is the transformer architecture powering current large language models. These systems are autoregressive, meaning they predict the next token in a sequence strictly based on statistical correlations found in their training data. This schematic illustrates the bottleneck of sequential decoding. Generating an output requires calculating a massive probability tree, step by step, token by token. This happens entirely in surface space. The model manipulates symbols without accessing the underlying physics of the objects they represent. Operating exclusively in surface space is the root cause of AI hallucinations. An autoregressive model can perfectly generate the mathematical equations for gravity because it ingested physics textbooks, but it possesses no physical concept of mass or velocity. When conditions deviate slightly from its training data, its reasoning shatters. Human cognition operates differently. Infants develop common sense through embodied experience, dropping objects and matting environments, long before they acquire language. Autoregressive models are eloquent calculators, but because they prioritize statistical mimicry over causal simulation, they remain blind to the laws of the physical world. Researchers are now building internal environment simulators that discard word prediction. Instead of guessing the next token, these systems track continuous spatial changes to understand their surroundings. This brain-inspired approach is championed by Yann LeCun through the development of the Joint Embedding Predictive Architecture, or JEPA. Traditional generative models waste computational resources attempting to reconstruct a scene pixel by pixel, getting bogged down by irrelevant details like the texture of a wall. JEPA rejects this. This diagram outlines the JEPA data flow. When raw video data enters the encoder, the architecture strips away the noise and surface details to extract only the abstract essence of the environment. That essence is mapped into latent space, a continuous mathematical plane capturing high-level semantic meaning. In latent space, the model understands that the lamp is off and the room is dark are not two separate pixel arrangements, but the same state. Because JEPA operates non-autoregressively in this latent space, it avoids the sequential bottleneck. It can predict entire future states in a single forward pass, making it highly computationally efficient. By shifting the focus from pixel reconstruction to latent feature extraction, the system moves past pattern recognition and achieves conceptual intuition. Building a latent space simulator introduces a severe engineering hurdle: representation collapse. Left to its own devices, an AI will attempt to cheat its reward function. To make its prediction task as easy as possible, the model will ignore the complex training data and collapse all representations into a single point, rendering its predictions meaningless. To prevent this, engineers apply a strict forcing function known as mathematical regularization. In architectures like LaJEPA, developers align the latent embeddings with isotropic Gaussian distributions. This mathematical constraint bursts the data outward, forcing the model to map diverse, distinct features from the real world. Once the latent space is stabilized, researchers use object-level masking in systems like Causal JEPA to teach the model true physics. By hiding parts of a video stream, the model must deduce what happens to objects it cannot see. When a shape rolls behind a barrier and the AI predicts it emerges accurately, it proves the system has internalized continuous physical momentum. Regularization and object masking strip away the system's ability to merely calculate words. They mathematically force the architecture to act as a physicist simulating reality. Translating this internal physics simulator into tangible action is the role of agentic AI. The model stops passively generating text and begins executing autonomous workflows. By late 2025, enterprise adoption of these systems moved from isolated pilots to scaled deployments. Organizations now employ AI agents to navigate software interfaces and execute multi-step logistics autonomously. This autonomy relies on chain-of-thought monitorability. The schematic shows how the model allocates extra processing time to verify its own logic step by step. Once verified, the logic gates route directly into a chain-of-action execution prompt. This verifiable reasoning has broken out of software environments and entered the physical world, driving robotics that navigate complex, human spaces. To operate safely in real time, these physical agents cannot rely on cloud server latency. They must run their models locally on specialized edge AI hardware. The hardware breakthrough making this possible is NVFFP4 quantization. By compressing models into a 4-bit floating point format, engineers drastically shrink power consumption while maintaining cognitive accuracy on battery-powered edge devices. Causal understanding, paired with efficient edge computing, is the catalyst that translates digital intelligence into autonomous physical labor. The success of causal reasoning and agentic architecture has triggered a contraction in expert timelines. Forecasts for artificial general intelligence and subsequent superintelligence have shortened from decades down to mere years. This acceleration exacerbates the alignment problem. As autonomous agents approach superhuman capabilities, the risk emerges that an efficient, misaligned agent could pursue unintended objectives with catastrophic consequences. Researchers divide this into two challenges. Outer alignment ensures the designer provides the correct initial goal. Inner alignment is the far more difficult challenge, ensuring the model actually adopts that goal robustly, rather than faking compliance while hiding its own objectives. To maintain scalable oversight, labs employ constitutional AI. This tree diagram shows the architecture. Model A generates a response or action, which is immediately routed into a codified parameter set, its constitution, supervised by a secondary model. Through reinforcement learning from AI feedback, Model B applies a reward signal back to the primary model based strictly on constitutional compliance. AI supervises AI, bypassing the slow bottleneck of human labeling. As these systems approach self-improvement thresholds, automated supervision loops stand as the only viable mechanism to bind superintelligence to human intent. At the macroeconomic level, the successful deployment of causal AGI systems is completely restructuring the global labor market. This graph maps the expected economic impact, known as the productivity J-curve. Measured productivity initially drops as firms invest capital into AI integration and workflow redesign. Once those investments mature, the trajectory arcs upward into exponential growth. Workers adapt into two collaborative archetypes to maintain relevance alongside autonomous agents: centaurs and cyborgs. Centaurs maintain a strict division of labor. The human acts as the strategic head, delegating tasks to the AI before verifying the output. Cyborgs engage in fused co-creation, where the human's thought process and the machine's generation loop continuously in real time. The massive shift from token prediction to world models represents a transition from software that talks to software that acts. Navigating the resulting surge in machine productivity requires a societal adaptation, a new way for humans to steer causal engines as they automate physical labor.